While everyone has been wowed in the last couple of years by the new rockets coming out of NASA and Blue Origin and SpaceX's Falcons, and more recently the tests of their Starship, an equally important side of our long-term space goals has been going on almost unnoticed. If you've ever watched films like Star Trek, you'll have seen the huge space docks where ships like the USS Enterprise are built and maintained in space. Now, of course, that's science fiction set hundreds of years in the future, but at some point, if we want to have larger and more useful habitats in space and even spacecraft, we're going to have to build them in space, instead of here on Earth and then launching them into space as we do at the moment. So how are we going to make and operate these space factories of the not too distant future? This video is sponsored by Magellan TV. Magellan is a new documentary streaming service run by filmmakers that have a passion for their work. They believe that science defines the cutting edge of society, and their mission is to tell great stories that define the human struggle to discover more. Magellan now has over 3,000 documentaries available, with more being added each week, with a wide selection of those in 4K for no extra cost. And you can also stream them directly to your smartphone or tablet wherever you are. As the subject of this video you're watching is about how we will start to build structures and spacecraft in space, then I think you'll enjoy many of the space-based documentaries Magellan has. One which I enjoyed a lot was Return to the Moon, looking at the preparations and how we will go back to the moon and hopefully stay there for the long term. You can watch this and many more by getting your 1 month free trial using the link for this special offer right at the top of the description below, and I'm sure you'll find Magellan TV as worthwhile as I have. Now, if you've seen almost any of the heavy lift launches in the last decade or so, then you'll have also noticed the oversized fairings they've been using. As payload sizes have increased, so have the fairing sizes needed to keep them safe until they make it into orbit. This has become known to some as the tyranny of the fairing, because it imposes a limit as to how large the payload can be, though through clever packaging and ingenious folding mechanisms, satellite and spacecraft makers have pushed their designs to the limit. Take for example the James Webb Space Telescope. When deployed, it will be much larger than the rocket fairing containing it, but once in space, unfolding it requires very complex mechanisms which must work perfectly when it's being deployed. Unlike the Hubble, which is only 540 kilometers above the Earth, the James Webb will be about 1.5 million kilometers from Earth. This means that if anything goes wrong with the deployment, like part of the folding mechanism getting jammed or damaged, there won't be a rescue mission going to fix the $10 billion space telescope. So, the carrying capacity of the launch vehicle also determines the size of the craft it's going to deliver. It would have been great to have maybe an 8-meter mirror in the Hubble, like the largest telescopes here on Earth, but there were no rockets that could carry such a large item, except possibly the SpaceX Starship, but of course that didn't exist at the time, and we don't quite know when it's going to be ready. Hubble's actual size and the spy satellites it's based on are all 2.5 meters, and that was determined by the size of a cargo bay on the space shuttle. If we could build such things in space, their size could be much larger, and without gravity to get in the way, we wouldn't have to worry about it collapsing under its own weight. Building things without gravity will lead to designs which simply cannot be built here on Earth, let alone survive the rocket ride into orbit and beyond. Whilst humans will be involved in the process, much of this will be done by robotics, and there are already companies that have been testing out such technologies on the ISS for several years. The process is called additive manufacturing and means that the humble 3D printer combined with robotic assembly is set to become one of the primary methods of space construction. US company Made in Space was the first to test a 3D printer on the ISS, allowing the crew to print specific tools without having to wait months for the next resupply mission. In 2017, they demonstrated the ability to 3D print structural beams in a NASA vacuum chamber, which mimicked the conditions of space to prove that it could withstand the vacuum and temperatures found there. Now, these are not going to be like the replicators in Star Trek, but it's a start. And in 2019, NASA awarded Made in Space a $73.7 million contract to demonstrate the technology in space. The NASA OSAM-2 mission, which is due to launch no earlier than 2022, OSAM meaning On-Orbit Servicing, Assembly and Manufacturing, is the NASA and Made in Space partnership, which will use Made in Space's Archinaut 1 spacecraft, which is about the size of a refrigerator, to construct its own solar panels once in space. One of the limiting factors to satellites is the amount of power they can have available to them. Large solar panels make more power, but even with the best folding technology, there's a limit to how small that can be and fit on a rocket, which limits the size of the spacecraft or satellite. Using new flexible solar panels that can be rolled up, the Archinaut 1 will construct the support beams, which would normally be folded up, by 3D printing them as the panels are deployed. Doing this in space will allow them to be much larger, and when fully built, they will extend 10 meters either side of a spacecraft, allowing them to generate 5 times more power than traditional folding panels on a craft of this size. The Archinaut is a customizable suite of manufacturing and assembly technology which can be integrated into free-flying satellites. Using this type of in-space manufacturing, you can see how much larger the solar panels on current spacecraft could be compared to how they are now. As the technology develops, it should be possible to build larger structures in space completely autonomously. Things like large space telescopes, communications antennas, radar booms, etc. Resupply ships would deliver the raw materials, allowing structures to be as large as practical. It could also be adapted to work on the Moon or Mars to build structures using localized materials, and as we venture further out, asteroids could supply raw materials like metals. But in order to make machines that will have to work unaided in places where no maintenance or repairs will be available, you have to have ultra reliability. However, things which we take for granted here on Earth, like bearings, gears, gearboxes, and the lubricants in them, can be a major problem in space because lubricants can freeze and cause mechanisms and gears to lock up. They also have a mechanical wear limit beyond which they will fail. By the time the Mars rover Spirit had become stuck in a patch of soft soil in 2009, 2 of its 6 wheels had developed problems, limiting its ability to extricate itself from the situation. If you try to build mechanisms without lubricants, in a vacuum, smooth metal with very flat surfaces can fuse together in a process known as cold welding. Lubricants in sensitive areas like filter wheels, in space telescopes and carousels that change instruments can also end up being deposited on highly sensitive areas. New work on what's called frictionless technology using superconducting magnetic bearings and gears where the components never actually touch each other is underway. These promise to do away with the need for lubricant, be immune to wear and friction, allow less precise alignment, and be able to work down to cryogenic levels in space, the very temperatures suiting superconducting magnets. The MagDrive, developed by the Spanish Madrid Carlos III University, is one such device that both ESA and NASA are looking at. Their magnetic gear reducer, a bit like a car gearbox, not only has contactless transmission, it also has input and output axles which levitate without bearings, allowing it to work at up to 3000 RPM down to minus 210 degrees Celsius in a vacuum. The transmission input and output shafts also self-balance, which eliminates oscillation and is the first gearbox in history that does not have that type of friction. A normal operating temperature version is also being developed here on Earth, where there is a need for use in a lubricant-free environment. Making things in space could also have benefits for us here on Earth. 2 companies, TechShot and 3D printer maker Enscript, are looking at making human organs in zero gravity. 3D printers can already construct early versions of things like blood vessels, bones, and cartilage in ears, using bioink comprised of human cells and other tissue which supports the growing organs. However, printing structures that are just 1 or 2 cells thick here on Earth, the pull of gravity can cause these tiny delicate structures to deform, which then need elaborate microstructures to hold them up. If these could be made in zero gravity, there will be no downward gravitational pressure deforming the structures as they grow. The long-term hope is that in the next 5 to 10 years, they will be able to create whole organs in space that will be able to be used here on Earth. These are early days, but the tyranny of the fairing may be coming to an end in the not too distant future, and then we can truly start to exploit the space above us. So thanks for watching, and I hope you enjoyed the video, and don't forget to subscribe, thumbs up and share. And before I go, I'd just like to thank all of our patrons for their ongoing support.